So is it true that any two odd numbers that you add, whether they're the same or not, is always going to equal to an even integer? Well, let's think about this, right? First thing you want to do when you approach a problem is think of some examples, because if you can't think of a counterexample, you're going to want to try proving it's true. So let's think of some examples. What are some odd numbers? 3 and 1. 3 plus 1 is 4. 4 is even. Okay. What about 7 and 3? Well, that's 10. What about 9 and 5? That's 14. All these two odd numbers that we add together is even. What if we try two of the same odd number? 3 plus 3, that's 6. 7 plus 7, 14. 5 plus 5 is 10. Okay, so with the first few odd numbers that you would think of, this is already seeming to be true, so let's try and prove it. First, we want to write this as a mathematical statement so we can better understand how we're going to go about proving this. So because we're proving any odd number, any means we're proving a for all statement. So for all two odd integers added together, the sum should be even. Okay, so let's write that down. For all, and let's call this A and this B, right? So we're going to say for all A, B that are integers. So for all integers A, B, if A and B are both odd, comma, then A plus B is even. Okay, great. So we have our statement. We now know exactly what we're going to take apart and try and prove is true. First thing you want to do, look at your statement, identify your P and Q. If P, then Q, right? That's what everyone's taught to think about. So this is our P, this is our Q. We're going to suppose P is true and prove that if P is true, then Q is true. Okay, great. So where do we go from here? Well, we need to know definitions of two things, right? Let me circle that in red. We need to know the definition of even and the definition of odd. Okay, well, what is the definition of even? Well, the definition of even is going to be some integer x such that x is equal to 2k, where k is also an integer. And you can think of some examples, test this against, I would say the first, any integer less than 10 is what you should really be testing these definitions in case you don't quite understand how they work. So think of 2. 2 can be written as 2 equals 2k. K in this case is going to equal 1. So yeah, k here is an integer. But if you do 3, right, 3 is equal to 2k. K here is going to equal to 3 over 2, which is not an integer, right? 3 over 2 is not an integer because it has decimal numbers. Okay, great. So we have our definition for even. Now, what we need is our second definition for odd. Odd is going to be defined as, now think about this, right? When you're thinking of numbers in the number line, it always goes even, odd, even, odd, even, odd, even, odd. And that's always going to be true. I'm sure there's some proof, and I might even do that proof at some point in the future. But for now, we can use that kind of logic to define odd. Well, if odd is just a number after even, we can just say odd is going to be x for some integer x such that x is equal to 2k plus 1, right? If we have an even number like 2, well, then the next odd number is going to be 3. If we have an even number like 14, the next odd number is going to be 15. You can just add 1 to an even number to make it odd. You have to not to forget to define your k. K is an integer. Okay, great. We have our two definitions we're going to be using, and we have our statement that we're going to focus on proving. Okay, we have everything we need to start. So, first thing we're going to do, notice it's a for all. What do we do for a for all? First word that should come to mind before you even start thinking is let. Let is the first thing you should write, followed by supposing P. So let A and B be integers, and suppose A and B are odd. Full stop. Okay, great. We supposed P. Next, what we want to do is we want to better define A and B, right? We want to say, what does it mean for them to be odd? That's how we're going to mathematically do this. So we're going to say A is equal to 2k plus 1, okay? Actually, let's use a different letter than k. Let's use m. 2m plus 1, and b is equal to 2n plus 1. And you have to, anytime you add a new variable, you have to define it. So we have to define m and n because we haven't defined them here, right? The reader doesn't see any of this. They just see this. A and b are integers, okay, a is equal to this, and then 2m and n. What's m and n? Okay, well, put a comma down and say m comma n are integers. Awesome. We can even put another let here if we wanted to. Or we can say, better yet, put a then. There we go. Then, and then let's put some other sentence in between. Math is all about writing sentences for people to be able to read. So then this is equal to that. So that m comma n are integers. It's really important to be writing this grammatically correct. Great. So we've introduced our variables. We defined a and b. Next, we want to get to ab is even. We want to say when this happens, this happens. So let's start with this, right? Let's say a plus b. Let's put therefore, comma, a plus b, unpack your definition slowly, is equal to what we just defined, 2m plus 1 plus 2n plus 1. I probably should put brackets around them like this, so it's more obvious that these are two separate entities I've just unpacked. But I think you're smart enough to see them, but I'll keep them here just for now. Now you should recognize when you add these two terms together, it's going to be 2m plus 2n plus 2. Okay, is there a way to get this to be an even number? The answer is, well, can we get it to look like this? Whatever we're looking at, x plus y, x, whatever, can it be 2 times some integer? Well, let's factor out 2 here. 2m plus n plus 1. Okay, awesome. So this is actually already proved that a plus b is even, because what you need to do is you need to recognize and explain to the user that m comma plus n plus 1 is an integer. I'm going to take for granted that we know that any sum of any integers, m plus n plus 1, is going to be an integer. You can't add 2 integers and get a decimal number. And because we know this, you can just say, since a plus b is equal to 2m plus n plus 1, where m plus n plus 1 is an integer, then a plus b is even. So the sum of actually any, since that's what we're proving, sum of any 2 odd numbers is always even. Great. We've just proven that adding any 2 odd numbers is going to make an even number or integer. Something I always tell people is you can be even more explicit, but some people disagree with this. I don't think it's very good because I don't want to write a whole lot. If you want to be super explicit, or if you don't see why this is true, you can simply, what you can do is erase this part. And what you can say is, okay, since m plus n plus 1 is any integer, we can give it another name, right? So we can say c is equal to m plus n plus 1. And we can say that because a plus b is going to be, actually we don't need to worry about that. So we can say then a plus b, I'll put a bracket around it so it looks like one variable, is equal to 2c. where c is an integer, and then you can argue that since a plus b is equal to 2 times c for some integer c, then by definition of even, a plus b is even. But the previous method is also true. You don't have to always say, oh, by definition, this is that. The reader, we're assuming, can understand that, oh, this is true because they know the definition of even, but you can remind them that this is because the definition of even is going to be that. So there we go. That's how you prove this statement.